Okay, so let's move on regarding Bayesian estimation, and also we will cover MCMC, at least the core of it in this video. Okay, so just a quick recap. We have prior distributions that are going to be specified. We also have data likelihood, and we need to obtain posterior distributions that in many times they are not available from analytical methods. So we need simulation-based techniques to get them. Okay, so MCMC consists in, first of all, the Monte Carlo method and also the Markov chain method. Here is Markov over here. And Markov invented a stochastic method to generate events. In this occasion, it will be numbers, where the probability of this event only depends on the previous event. That's why they are called chains, because they are numbers that are chained with each other, okay? And they can't just be extended to infinity. Okay, so the Monte Carlo method is also a method to generate pseudo-random numbers. So this is pretty accurate and useful for what we need, that is basically generating probability distributions. So let's use this example. As you can see here, we have a prior that is a bidimensional prior that can be plotted like this and also like this. We will also have a data likelihood distribution that is like this. So we will have a posterior like this. Okay, so our objective is to reproduce or to create something that is very similar to this ideal distribution of the posterior, because it's not available from analytical methods. Okay, so the first way to make a MCMC to work was proposed by Metropolis over here. That was made for Boltzmann distributions, but the generalized form of the algorithm was proposed by Hastings. So that is why it's called the Metropolis algorithm, or also the Hastings Metropolis or Metropolis-Hastings, because they were the two main figures to develop this one. This is a graphical representation of the Metropolis-Hastings algorithm, as you can see here. So it's not super accurate to recreate the posterior, but remember that we don't need for it to be super precise in the global form, because we need a point estimate like MAP, median, or something like that, a highest density interval, and their derived products of that, for example, a bias factor or something like that. Okay, so as you can see here, we can get a similar form, enough similar to the posterior, the ideal posterior, to maybe have a very precise measurement of our point estimate and or highest density interval. A posterior way to make these MCMCs to work was called the Gibbs Sampler. The Gibbs Sampler is a special case of the Metropolis algorithm that is very useful if you want joint distributions, just like this one, because it's a bidimensional joint distribution of two parameters, θ1 and θ2, and also developed posteriorly by Giemann and Giemann. This is especially useful, this method is especially useful if the joint distribution cannot be obtained analytically, but we can estimate its components. Therefore, the posterior distribution of θ1 can be obtained, and θ2 also can be obtained, but we cannot obtain θ2. Therefore, this algorithm can be very useful. This is why it is so widely used. So this is a graphical comparison of what we can get using Gibbs Sampler. Here is with intermediate steps only, and here is with full steps. So as you can see here, more or less, they get a very similar result to the Metropolis algorithm. However, as you can see here, it's kind of more precise without the little groupings of Metropolis. For example, here you can see the little groupings or the mini clusters that are present that are not present here or here. Everything is kind of colliding into a global shape. Okay. However, Gibbs Sampler requires normally more steps, therefore it's more time and more computational power. And we know that both methods converge in infinity. So if we have enough power, it doesn't matter. So the only difference is that they get to the same place, but they differ in the specific steps they make. Okay. And as I said earlier, normally our goal is to have a precise point estimate and also a precise highest density interval. And as you can see here, these estimations are very similar between each other. For example, the mode estimation is like 0.3 something. The only one that is a little bit different is this variation of the Metropolis algorithm with 0.28 or 29. And the highest density interval is also very similar between methods. Therefore, as you can see here, there are maybe some technical differences in applied examples, and therefore you need to be mindful of these methods, but normally they are not a big of a deal. Normally the default Gibbs sampler, it's enough to get yourself the posterior distribution that you need to make the inference, okay? So this also can be employed for bias factors and also sequential analysis and robustness analysis. So this is the essential pack, the core of MCMC. So now, following this, we will see how to diagnose that everything went well in this Markov Chain Monte Carlo method.